Okay, we're going to move today into section 6.2 now, and this is addition, subtraction, and estimation. We talked very briefly about estimation in the last bit of that last section when we were sort of looking at those comparable fractions. And what we're going to take a look at now is we're going to look at adding and subtracting the estimations at the end. The first note that this talks about is it does kind of like what we were doing when we had similar or same denominators and we were comparing. So if we actually already have the same denominator and we want to add fractions together, we just need to add the numerators together. And this works very well to be able to show that this works with some kind of an imagery. Maybe you want to use a pie or a circle, and you talk about adding the numbers 1/4 plus 2/4, and just for the moment I know 2/4 is 1/2, but it'll be easier if I kept denominators the same to make the argument. And so we're going to split this image in pieces. That's not right. Hang on. So as we talked about last time, okay, I can't get my line to draw right. The pieces need to be equal. I think I got them okay. And so if we're talking about 1/4 of the picture, we're talking about one corner of this. If we're talking about 2/4, we're talking about two corners. And then very clearly you can count them up and see that yes, in fact, if I add the 1 plus the 2, I get the 3, and there are 3 pieces shaded in. Okay, so it's very simple to argue that this would work. Unfortunately, not all fractions have the same denominator. However, in order to add them together, we need them to have the same denominator. There's several ways to do that. We've talked about getting denominators the same in the last section. We talked about getting a common denominator. We also talked about getting a least common denominator. And depending on the fractions you're working with will kind of help you decide which one of those two methods you would like to use. This is actually another way of thinking about it. It gets you a common denominator is what this is doing, but it has a really nice visual appeal to it. And I had not seen it before your book did it. I simply wasn't taught the way that the book is showing this. But I think it's pretty cool. So I wanted to show it to you because you're going to have students who are going to be very visual in your class. And they're going to see something like this and they're going to be able to cling to that really easily because they think about it visually. So what this actually does is it multiplies across this diagonal and it writes down A times D. And it does the plus sign. Multiplies across the other diagonal. Multiplies to B times C. And then it multiplies across the denominator. And the net effect is simply multiplying the first fraction by D over D and the second fraction by C over C. It's the same thing, but it's sort of hidden in the midst of what's going on in a very visually appealing way. Okay? I put this note at the bottom because you probably are aware of it, but just in case you hadn't thought about it in this way, adding and subtracting fractions is really hard for kids. Multiplying and dividing is much easier. But the addition and subtraction is very challenging. So when students don't like fractions, this is usually why. So the addition and subtraction is actually often taught after the multiplication and division in most middle school or even the higher grade school textbooks, depending on where they're finding it. Okay, they usually encounter the multiplication and division first. Your book's using the addition and subtraction first, so we're going to do that. But all right, we're going to do a couple of these. So I've got 1/3 plus 5/3, which would give me a total of what? 6/3, and we're not going to leave it that way though. So what are we going to change it to? Yeah, this is the number 2. So as we're working on most of the time, there are occasions where we might leave a fraction in unreduced form. Later on in the semester when we get to some issues with ratios, we may see that happen. But for the most part, we will simplify our fractions unless there's a reason not to. All right, the second one, they don't have the same denominator. Okay, so let's do this a couple of ways. I'm going to show you the one that I just did that was really nice and visually appealing. And some of you probably thought this is silly, but that's okay. You can think it's silly. So I've got 1 times 3, so this is 3. Plus, I've got 4 times 5, which is 20. Over, and then I multiply the denominator together, 4 times 3, which is 12. And then I'll simplify by adding the two pieces of the numerator together to give me 23 over 12. Now, at this point, a good place for me to insert how you decide what to do when you get to your final answer. So we just said we're going to reduce, and this one doesn't actually reduce. That is, the 23 and the 12 don't have anything in common, right? However, I do have a numerator that's bigger than the denominator. Yeah? It's okay. You can have a numerator bigger than the denominator. All right? So unless there is a reason to change it into a mixed number, and I'll show you when we encounter that, then there's no reason to do so. So leaving the 23 over the 12, even though it's top heavy or it's an improper fraction, it's okay. Improper doesn't mean it's bad. It just means that the numerator is bigger than the denominator. Okay, so we can leave it here just like this. Now, if you don't like doing this, or if you wanted to show another student what was really happening, maybe they said, okay, that's really cute, because you're going to have some of them who are going to be like, but why? Why does that work? All right, you've had those students, maybe you are one of those students, and you can actually show them why that works. Well, it works because what you're really doing is you're really multiplying the first fraction by 3 over 3. And then your second 5 over 3, you're really multiplying that 5 over 3 by 4 over 4. Right? So in essence, what you're ending up doing is you're getting 3 over 12 plus 20 over 12. And then you can actually sort of, harken back to the fact that the denominators are the same. So we simply add the numerators together to get 23 over 12. It really doesn't matter to me which one you like or even which one you use, but you should be aware that there's more than one way to think about it so that you'll be able to explain it in more than one way when you get in a classroom. Okay? All right, so there's those mixed numbers that I just mentioned, right? All right, so mixed numbers. From a mathematician's point of view, mixed numbers are annoying. I don't like them. I find them to be obnoxious. Unfortunately, they are very common in real life because this is how we think in real life. Mathematically, they're not fun to work with, but in real life, they occur everywhere. I mean, I don't say I have 5/3 of a cookie. I would say I have 1 2/3 of a cookie, right? I mean, that's how we think when we look at the cookie. Unless if we were a bunch of pieces, we might count 5 pieces, but that's not what we're usually encountering. So we have here, I ate 2½ cookies is the example I gave on here. 2½ is 5/2, but we would never say I ate 5/2 of a cookie. I ate 5½ cookies. We don't talk like that. So there is good reason to be able to think back and forth between these. One, because one of them is the one that we think in real life, and the other one because it's much easier to do mathematics when we have the improper fractions in certain situations. So first we're going to take this 14 over 3 and we're going to turn it back into a mixed number. Okay? So if we're asked to turn something into a mixed number, 14 over 3, you want to remember that that over part is actually division. So really we're just dividing 14 by 3. And we're going to look at what we get. So how many times does 3 go into 14? 4 times, which gives me 12. And once upon a day you were allowed to put 4R something. What's the remainder? The remainder is 2, right? Okay. So writing it then as a mixed number, which is what you were indicating, is that we write it as 4 2/3, because the remainder 2 is 2 out of the 3 we started with. So this would be the mixed number that corresponds to the improper fraction 14 over 3. We're going to go the other direction now. We're going to take a mixed number and turn it into an improper fraction. First of all, let me say that the negative at the beginning doesn't affect the process of it. The answer is just going to have a negative. So I'm going to ignore it till I get to the end. Okay? So the 8 and the 3 and the 5, let me show you how we think about it and do it like in a process-oriented way. And then I'll show you why it works, because it looks, again, a little bit like magic, and some kid's going to ask you why that you were able to do that. So let me show you what we practically usually do, in case you have forgotten. Practically, we say, let's take 8 times 3, and we would get 24. And then we're going to add that to the top, which gives me 29, and we're going to write that over the same denominator. Okay, everybody remember that that's how that works? Oh, and it's negative because I started with a negative number. 29 over 8. Negative 29 over 8. I'd like to talk to you about why that works. Okay, so the 3 and the 5/8, when we write it as 3 and 5/8, we really mean 3 plus 5/8. I've got 3 whole cookies and I've got 5/8 of another cookie, something like that. Well, if I wanted to add these two together, the way we added things together in the last slides, I would write that 3 as something over 8, right? Get a common denominator. So I would actually write that as 24 over 8. So that's why we're able to do this 8 times 3 business over here. It's because I'm really just getting it to have that denominator of 8. That gave me the 24. And then I can add across the top because they have the same denominator. So that becomes the 29 over 8. Okay? So we've got this sort of visually appealing way, but it actually goes back to adding and subtracting fractions is what it goes back to. And again, it's all negative. I have negatives that I've sort of ignored along the way, but they're all negative. All right. Additive inverse. This is a property of rational numbers. It's a property of integers as well. All it says is that if you have a fraction, a over b, that there is a unique rational number, negative a over b. So when you add them together, you get back to 0. And you guys know this, because if I gave you the value 6 over 12, let's do 6 over 13, just so it's not reducible, 6 over 13, then you'd be able to say that the additive inverse is negative 6 over 13, because 6 over 13 plus negative 6 over 13 is 0. And this works for every number except for 0 itself, right? So at least we don't have the same sort of a feeling of putting another negative with it. It works for 0. It's just that 0 is its own additive inverse, right? 0 plus 0 is 0, that kind of thing, which sort of feels funny. But all rational numbers have this ability. We have the ability to talk about them in this way. And we could start out with something negative, right? So I could actually start out with negative 24 over 73 and ask you what its additive inverse is, and you'd say it's positive 24 over 73. You just use the positive part of it, okay? So there's a positive and negative sort of pairing of these values together. Additive property of equality. This is actually used when you're talking about balancing things. So they're talking about balancing an equation in this particular case, but you could use any kind of a balancing situation you wanted to. So imagine balancing scales or something like that. All this is saying is if you have two things that are equal to start with and you add something to them that's the same, that they're still going to be equal, right? So for instance, if we wanted to talk about your height, so if I stood up here and I had one of you guys stand next to me, then we both put on 2-inch heels, we'd still be the same difference in height that we were to begin with, right? Or if we were the same to start, we'd still be the same after we put on those 2-inch heels. All right, so that's all that this is saying. And so there's nothing in particular special about it, but we do use this property an awful lot when you get to solving equations. And we're going to do an example of that now with an equation. So this is, yes?
When we are solving this like on an exam, will we need to say this is theorem 6-9?
No.
Additive? Okay.
No, but I'm going to show you what you're going to write next to it that's going to justify your answer, and I think that'll answer your question too. So, yeah, so we've got this equation, and it has mixed numbers in it, which is not my favorite, as you already found out very quickly. But we're going to solve it using that last property that we just encountered. That is, you know, with solving equations, the goal is to get it to say x equals something, right? You want the x by itself, all the numbers on the other side, whether that means you add, subtract, multiply, divide, square root, whatever it is that you're having to do, you want x alone. Well, on this one, the x isn't really all that far from being alone, right? So what we're missing is we're missing this 2.5, or what we've had extra, I guess you could say, is this 2.5. We don't want that 2.5 over there on the left-hand side. So what the last theorem told us that I'm allowed to do is I'm allowed to add 2.5 to the other side, both sides, in fact. So what I'm going to do is I'm going to add 2.5 to both sides of the equation. So I'm adding this to both sides. And the reason I can do that, and there are places where they're going to have these sort of lines next to something where you have to justify why you can do certain things. This works because of the addition property of equality. Okay? It has a number, but that's just textbook dependent. The reason that works is because there's an additive property of equations, of equality. Now, what's happening next is a little bit more interesting. There are two ways to add 2.5 and 3 1/3. Okay? So I want to show you both ways. Chances are you learned one of them and maybe not the other. And it always surprises me because it's not always the same. So half of you, maybe not even half, maybe a third of you learned something and 2/3 of you learned something else. But you should be aware that there are two ways to actually add these values together. I'm going to show you the way that I was taught first, and it's actually not my favorite way. I like the other one better. The way I was taught to add fractions together is to turn them into improper fractions, right? Make them top heavy, then get the same denominators, add them all together, and simplify when I'm done. That's the way I was taught. Okay? So I'm going to show you that way first. So we're going to start with these values that we're given. This is 2 1/2 and 3 1/3. They're not terribly ugly fractions to start with. But they don't have the same denominator, which means we're going to have to do a little bit to get that to work. So I'm going to change them into mixed numbers. So 2.5 becomes what? 5 over 2. Yeah, careful. And then the next one, 3 1/3, becomes 10 over 3. We'll go ahead and use that sort of visual way of multiplying the fraction or adding the fractions together with the multiplication pieces. So we'll multiply across the first diagonal 5 times 3, which is 15. Second diagonal 2 times 10, which is 20. And then across the denominator, which is 6. So 15 plus 20 is 35. And then over 6. Now, I told you before that there's no reason you have to change, or that I would show you when you needed to change something back into a mixed number, or change it into a mixed number. This is when you would do that. And let me tell you why and how you'll know or be able to identify that. 35 over 6 is a perfectly legitimate answer if the original problem had started out as improper fractions. But this original problem started in mixed numbers. So the answer needs to be in mixed numbers. It's kind of like somebody telling you how much something is in gallons, and then you respond something else about how much something is in liters. That's not how the question started. It's not how you were asked the question or how things were posed originally. So however the problem starts is how the problem is going to end. So I need to change this back into a mixed number because it started out that way. So I'm going to take 35 and divide by 6. How many times will 6 go into 35? 5. Which then gives me a remainder of 5, actually, yeah. So my actual final answer is 5 and 5/6. So this is sort of method number 1. It's the improper fraction method. That's what I'll call it. Because that's what we're doing. We're changing them into improper fractions. Now, when denominators are small, when the fractions themselves are fairly simple, this actually works pretty quick, and it isn't too bad. But if you've got several fractions and all that have different denominators, and the fractions are sometimes larger or the denominators are bigger, it can get really ugly. Okay? So I want to show you another way that works as well, works a little differently. So this other approach is actually a mixed number approach. Okay? So we're adding 2 1/2 to 3 1/3. So in this method, what we do is we add the whole numbers together first. So what's 2 plus 3? 5. And then we're going to add the 1/2 and the 1/3 together. These don't have the same denominator, so I still have to get a same denominator. So I don't sort of get out of that. But I don't have to deal with the 5 part at all. It's just going to be part of the answer at the end, 5. And you see where it is, right? It's right here at the beginning with this 5. Okay, so I never had to deal with that in terms of changing it. All right, so this other piece then, I'll do this sort of a visual method. So I'm going to have 1 times 3, which is 3, 2 times 1, which is 2, and then 2 times 3, which is 6, which gives me 3 plus 2, or 5. I'll write it that way, 5, over the 6. And another way, of course, then, of writing 5 plus 5/6 is 5 and 5/6. I'm really a fan of that because it keeps the fractions smaller, and I kind of like that. Not everybody is, though, and that's okay if you're not. But it is another option. All right, definition of subtraction. If a over b and c over d are rational numbers, and we talk about taking a over b minus c over d, this will be the unique number e over f, such this following equation is true. And I just want to use some whole numbers to show you this because you know that this is how it works. It just looks a little funny with all the letters everywhere. All this is saying is that if you have 5 minus 3 and it equals some unique number 2, the reason it equals 2 is because you could have had that 5 to start with, and you would have had to add 2 to the 3 to get back to 5. That's all this definition is saying, is it's the piece that's not there. The reason the answer is 2 is because if I actually consider, and this is usually how students are actually taught to subtract to begin with, is they're saying, I have 3, how many more do I need to get to 5? And that's what you're actually seeing happen in that particular definition. This next piece right here is actually also telling you that if you have subtraction, a over b minus c over d, it's the same thing as adding a negative value. They're an equivalent, equivalent operation. All right, so we're going to do addition. We're going to do subtraction like we did addition. So the subtraction of rational numbers with like denominators works the same way. If they have the same denominator, we can just subtract straight across the numerator. The second one, the different denominators, is if we have different denominators, we can do this cross multiplication kind of thing, or at least diagonal multiplication or whatever, and multiply across our diagonals. The only difference, of course, is that since it's subtraction, it's subtracted in the numerator instead of added in the numerator. Okay, so we're going to do an example with one of these. And this example gets a little bit more complicated because there's more numbers involved. Martine bought 8 3/4 yards of fabric. She wants to make a skirt using 1 7/8 yards, pants using 2 3/8 yards, and a vest using 1 2/3 yards. How much fabric will be left over? Okay. There's a couple of different ways to set the problem up, so somebody give me a suggestion and we'll go with what you think. What could we do?
I would add the ones that she's using together, and then subtract that total from 8 3/4 yards.
So you want to add those together first, and then in essence subtract them from that one. Does that look good?
Yes.
Okay. I think that's a good way to do that. So we're doing it in sort of two different steps happening there. All right, so notice, however, that, well, we do have two of the denominators the same. Two of the denominators have 8s in them. The other two are not the same. They're a 3 and a 4. So we're sort of back to the same kind of problem that last example was, where I had the mixed numbers going on, because I have mixed numbers that don't have the same denominator, and I have to decide how I want to approach the problem. So I have a feeling, just because of the way I was looking at some of your faces, that that second approach is probably the one that the fewest of you had seen. Am I right? So most of you, it looked like, had seen the improper fractions one and maybe not seen the mixed numbers one. Okay? So is it okay with you if I show you how this one works with that mixed number one? Would that be all right? Okay. So we're going to take a look at adding these together. That's going to be the same thing as we just did on the last problem. So we'll add those together the same way. So we're going to add the whole number parts together so that we can just focus on the fractional parts as they are to add those together. So I have 1 plus 2 plus 1. So that's 4, right? And it's actually kind of nice. 2 of them are already the same denominator, so I could go ahead and add those together right now as well. So I have 7 over 8 and 3 over 8, which is 10 over 8. 10 over 8 has a couple of unique things going on with it. Can somebody identify one for us?
Reduce.
It can reduce. What else? It's what? It's top heavy. It's bigger than 1, right? So it actually could change into a mixed number as well and make things easier to work with. We could actually simplify it in both of those ways. So we're going to do that because, and if we don't do it now, we'll have to do it later. So it doesn't really matter when we do it, but it's kind of nice to do it now. So the 10 over 8, first of all, let's reduce it. So what does it reduce to? Okay, 5 over 4 first. Is that okay if I do that? You guys are going, a couple of you are going in the other order, which is fine. But then that turns into the mixed number 1 1/4, right? And I kind of like the fact that this turned into something over 4. Why would I like that? I already have something over 4 at the beginning of the fraction, that 8 3/4, right? All right, so this is kind of nice at this point because I've got another mixed number that I can make the fraction smaller. So I've got the 4 plus the 1, so I've got 5. So here's my 8 3/4 minus 5 plus, and then I've now got the 1/4 plus the 2/3. Okay, so visually we can cross the diagonals. I have 8 3/4 minus 5 plus, so I've got 3 plus 8 over 12. So what's 3 plus 8? 11. So now 8 3/4 minus 5 and 11 over 12. Okay, so far so good? Okay. Now what?
Subtract your.
We have to be a little bit careful with the subtraction. We didn't have to with the addition, but we do have to be a little bit careful with our subtraction. Let's change the fractional parts to have the same denominator so I can show you where we're going to run into a little bit of problem when we didn't have the problem before, okay? So let's change that 3/4 into something with a 12 down there. How would we do that? Right. So I've got 8 and I've got 9/12 minus 5 and 11/12. Now, if I pair them up like we did before with the addition, that's going to give me the 8 minus 5, which is perfectly fine. But then I'm going to get 9/12 minus 11/12, which again is okay, but what's going to happen here is what? I'm going to have to borrow or I'm going to get a negative. Agreed? Because the 9/12 is smaller than the 11/12. So we can do that one of two ways. I'm going to deal with it as a negative for the moment, and then we'll do the borrowing that Carrie Ann just suggested in a minute. So the 8 minus 5 actually is going to be our next step, as you guys mentioned. 8 minus 5 is going to give me the 3. And then what I actually am going to have is I'm going to have 9/12 minus 11/12, which is negative 2/12, which is 1/6, yeah. So let me write it as the negative 1/6 just because you guys mentioned it already. If you don't do it now, you're going to do it later anyway. So, I mean, this doesn't exactly work, right? I mean, with addition, I would just mush them back together, so to speak, and I'd have my answer. But now I've still got subtraction in between them. So, again, one way to handle that is to do something with a borrowing sort of a strategy. 3 can actually be written as 2 plus 1. And I can talk about 1 minus 1/6. And 1 can be thought of either as the whole number 1 or as the fraction what? 6/6. Yeah. So my final answer ends up being 2 and 5/6 what? Yards. Yeah. Make sure that if you're dealing with a problem that has context, that the answer also has that same context. So you have 2 and 5/6 yards.
Could you do this if, like, the student doesn't know to do the stuff in parentheses first? Like, would you have to, like, make sure they know how to do that first, or would you just kind of tell them as you're going?
They would have encountered order of operations before they would have encountered doing this, yes, the idea. And we could also talk about in terms of context on this particular problem, that we're sort of adding up all the pieces that she needs to do her projects first, and then we'll see if she has enough material to actually do those projects with the subtraction, so you could also approach it in that way.
Okay.
Yeah. All right.